Hello friends, welcome to this video, and in this video we are going to use U2Net for the purpose of image mating, and all this program would be built using the TensorFlow framework. So let's get started. So first of all, we'll learn about the U2Net. I already have a video on the implementation of U2Net in the TensorFlow framework. So to learn more about it, you can watch that video after this. So let's revise it in short. So U2Net is an architecture for salient object detection. So what do you mean by salient object detection? It is basically the process of extracting main object from the entire image. This U2Net is a two-level nested U-shaped architecture built using the proposed residual U block. And the main thing about this architecture is that it does not use any pre-trained backbone like many other networks, because using a pre-trained backbone has its own disadvantages. So to learn more about U2Net, I recommend you watch that video. But if you haven't watched that video, don't worry about it. You can watch it later. In this video, let's learn how to train it, okay, for image mating. Our next question is, what is image mating? Image mating is the process of accurately estimating the foreground object in the images and videos. It's a very important technique in image and video editing application, particularly film production, for creating visual effect. Here you can see an image on the right side. You can see image and their respective mask or mate, I think they call it. Here you can see it is much different from a normal segmentation ground truth. We see here, because in image mating we have fine objects which we need to segment really carefully. So one major question you're gonna ask or thinking about here, what is the difference between this image mating task and image segmentation? So let's dive into this. Okay, so in image segmentation, what we particularly do, we divide or categorize a pixel into a specific class. Let's say we are working on binary segmentation, so we're gonna have two classes, a main class and a background class. So main class would be represented by 1 and background class 0. Okay, so in image mating we don't do that. We don't classify a pixel. We just want to predict the proper value which can segment both the background and the foreground, because in some cases if you see those hairs are not properly background nor the foreground, so there's a in between value then. So there's a value in between which would properly make things like they are working fine. Okay, I hope you just get it. If you don't get the difference, please comment below. I'll write a detailed post on it. What is the difference between image mating and image segmentation? So now let's move forward. So what is the data set which we have used? So the name of the data set is privacy preserving portrait mating dataset, and it contains 10k images which are high resolution real world with face blurred portrait images along with their manually labeled alpha mates. Okay, so here in image mating we call the prediction as alpha mates basically. Okay, so here you can see some of the samples. If you see the training sample, they have face blurred, and if you see this, the below images, they are from the validation set where you have two options: one where you have original images, second where faces are blurred. So let's have a look at the data set first. This is the complete dataset directory which you get after you downloaded it. So to download it, check the description. I'll provide the link there. So let's move into the training. Simply I'll show you how we're gonna work. So these are the blurred images. So let's wait. Yeah. So these are some of the samples. You can see all of them have their faces blurred. This is to preserve the privacy. Okay, and you also have the mask of these blurred part, and here you can see the mask. So mask basically means alpha mates. So these are the alpha mate for those human object, because these task is for portrait mating basically. Now these are the ground truth for those images, and same we have in the validation set. Now here you can see two folder. Here NP means known privacy and P mean preserving privacy. So here you can see original images. So here the faces are not blurred if you see, and we have their mask, alpha mates basically, and here we also have try maps. The try maps are basically the mask, you can say, where we have this three classes. So white one is the main object, black one is the background, and this gray part is basically intermediate, where we have both the background and the foreground class. So to make it easier to algorithm or the architecture to understand, some method use try maps also, but our U2Net does not use try map. It directly take images and work with them. And here P means privacy. Let's see the blurred images now. You can see these images are blurred. Okay, now these face masks I'll show you. For train, let's see. Okay, here you can see. So this is the mask for the face blurred, where you can see in the blurred images the faces are blurred. So those blurred for that blurred face, this is the mask. Okay, so this is given so that you have all the necessary dataset images and thing with you. Okay, so we are done with the dataset explanation. Now we'll move on to the implementation part. Let's work on the code. So I already have the architecture here, which is U2Net. So I'll not explain it here. You can watch that video separately. So what I'll tell you here, we have two architecture. First is this U2Net and second is this U2Net Lite. Okay, so you can use any, but let me just run this build U2Net Lite version here. Okay, let me just zoom it so that it's easy for you to see. Okay, so let us run and check if there's any error. Okay, you can see things are working fine. Okay, now let me just give you a brief about this. So what we have initially, we have this input layer, that is the image. Okay, we have some layers in between, and we have the output. So let's go to the output. So these are the 7 outputs we have. Okay, we have y0, then y1 till y6. So in total 7 output we have. So let me just show you one. So if you see this y0, okay, this is the y0. So y0 is basically our final alpha mate. Okay, is our final prediction, because this is a combination of all the prediction y1, y2, y3, y4, y5, y6. Okay, and from where these y1, y2, y3 comes, so see, y1 is from d5, y2 is from d4. So just imagine d5 as the decoder 5, d4 as the decoder 4. So it's basically deep supervision. Let's go back to the architecture. Here you can see this is the y0. You can see the concatenated version. No, this is the concatenation of all the masks, and this is the y0, the fused mask. And here you can see this is soup1 refers to y1, soup2 y2, and like this. Okay, so this is basically deep supervision. So this is just important to tell you before we move on to the training part. So here we can see our architecture is working fine. So we'll directly jump onto the training part. Okay, so first of all, what we'll do, we'll import all the necessary libraries and functions which we require. Okay, can see we have imported the OS library, then we imported NumPy because we are dealing with images, and when we read image using OpenCV, they are read as NumPy. Then we have globe, this we would use in the data extraction when we're going to extract all the images and their respective labels. And after that we have this shuffle function from sklearn, and after that we have TensorFlow and some of its functions. Now let's import our architecture. So we have imported both U2Net Lite and U2Net, okay, not U2Net, U2Net and U2Net Lite. Now we'll define some global parameter at the starting. This is basically height and width. Okay, so our input image would be of height and width. This is 512 by 512. So you can set this accordingly. Okay, because I have really good GPU, that is 3090 24 GB, so I can, my GPU can handle this size, but maybe your GPU cannot handle this. So just choose your size accordingly. So don't just fix this size specifically. Now let's create a function here called create dir. So what this function does, it takes the path and it check whether this path exists or not, and if it does not exist, it's gonna create that path. So basically we are creating a folder whenever required with this function. So let's say if not os.path.exist. So if this path does not exist, then right, make dirs. So this is really simple. Now let's start with the main function from where the execution starts. So first of all, we'll seed the environment for the purpose of reproducibility, because neural network have randomness in them. To make sure we have same randomness every time, we seed the environment. I think seeding works best in PyTorch. Now it's fine with TensorFlow also, but still I face some issues with TensorFlow, I think. Okay, next we're going to create a directory called files to save our weight file and other required things. Next we'll define some hyperparameters. So we have defined a batch size of 8. Now again, just don't fix this. Maybe you don't have same GPU as mine, so this batch size won't work, because working with 512 by 512 with batch size of 8 requires good amount of GPU memory. So just see if you receive any OOM error. OOM refers to out of memory. Just remember this OOM error. Whenever you have OOM error, most of the time which I've experienced is because of the batch size. You need to decrease it and it's going to work fine. Okay, next we have learning rate, number of epoch. Then here we have two paths. So first is the path for our weight file. So this is the path where we will save our weight file, that is model.h5. Then we have our log.csv. So this log file would save our training and validation matrices during training, so that later we can see. Now next we have our dataset path. So this is the path for the dataset. To download this dataset, please check the description. You'll find the link for the dataset there. And if that path of the dataset is not there, you can easily search it with the name, or you can comment it below. I'll try to provide you a link. Okay, now we'll work onto the data processing part. So in data processing, first we'll load the dataset. So let's write name a function called load dataset, and it take the dataset path. So let's work on this. Load dataset, first path. This is, so what we do, we'll first load the training images and labels, then validation images and labels. So let's call training images train X sorted. I'll tell you why I write sort here, why I'm going to sort this output of the globe. So output of the globe would be a list, and I'm going to sort the list because we're going to have image and mask pair. Okay, so whenever I say mask here, it means the ground truth of the image mate dataset. Okay, because I mostly work with segmentation, so whenever some ground truth came in, I generally says it's a mask. So don't get confused, it's basically mean the same. So we'll write path here. Okay, not like this. We have os.path.join. Okay, so just one more thing here. I am using an Ubuntu. So slashes are different. You are using Windows, then the paths would be the major cause of issue. So just please check it. Okay. Just print the path and see if it is correct or not. Just that simple thing you need to do. So let's join the path. So let me show you the path. So first we are here in the path, then train, blurred images, and inside we have all the images. So this is the path. So what we'll do, say train, then we have blurred images. Let me copy this instead of writing it down incorrectly, having error. It's better to copy paste it. So this is our train X. Now we'll have our train Y, that is the ground truth for the images. Again we're gonna sort this list written by the globe function. So we sort them basically so that we have same sequence of images. Okay, let's say start with 1 2 3 4 5 6. So same sequence should be in both the train X and train Y. This technique works when you have same name for image and ground truth. Let's say you don't have same name, so this technique won't work. Just keep in mind. Then you need to find some other way, make sure that it works. Now we'll load the validation set. I'm directly copy pasting it. So if you see, I'm using np, non privacy, as the validation. Is up to you what you want to use. Okay, so let's move down. So what we'll have this data set here. Now we'll print the number of images and their ground truth for both training and validation. We'll print the length of this list basically. So let me run this till here and see if we have any issue. Okay, you can see we have 9,421 images for training and 500 for validation. Now we'll work onto the data processing, where we'll work on the data pipeline, which will be used for training and validation. So first of all, we have a simple function called read image, which takes the path. Okay, so here what we have a path which is encoded. First we're going to decode it, read the image, resize it, normalize and give it back. So we say path equals to path.decode. Then we're going to read the image. Okay, and we're going to read it. So this is I am read path, and we're going to read it as RGB image. So we have read the image. Now we're going to resize it X. So when you use OpenCV to resize images, just make sure you put width first, then height. Yesterday what I have done, instead of writing CV2 here, I have written NP by mistake, and I'm like confused why this is not working, because I specifically remember the thing that during if you use CV2.resize, you put width first, and I put width first because I did not focus on this, that it is NP, and I have wasted like 10 minutes. Why this thing is not working? But finally I managed to see what mistake I have done. So mistakes are just part of life. If you're doing mistake, this means you are at least doing something. If you are not having any mistake, it means you have perfected the thing, or you are not doing new things, you are just focusing on the old stuff which you already know, or you aren't trying anything. That's why you don't get any mistake. Now we'll write another function called read mask. So it is also basically same as above. First we're gonna decode the path. I'm gonna copy it from here. Then we're gonna read the image, but this time we're gonna read this not image, basically image. We're gonna read this mask as grayscale because this black and white, so we're gonna read it as grayscale. Next we're gonna resize and normalize it. Now we're gonna change its data type, expand its dimension, and give back this. So when we read image using this as RGB, what it gives, it gives it as height by width by, then we have number of channels. And if we read it as grayscale, it's gonna be height by width. So when we add this line, this changes to height by width by 1. This is the simple effect. Okay. Now what we'll do, we'll write one more function. Not one, we need two more functions for this data pipeline. See, we are writing some extra function just because I'm using OpenCV. If you write this entire thing in TensorFlow, it would be easy, but I usually prefer OpenCV. At least, like in case when I need any function which is outside TensorFlow, I can easily integrate it here. So that is why I usually prefer OpenCV NumPy thing. Note, I don't use everything from TensorFlow. So we're going to read image here from X, Y is equals to read mask Y. Now we're going to give both these X and Y back. Now, because we have used this OpenCV and NumPy, which is outside the TensorFlow framework, so we cannot directly use these two functions. So what we have done first, we have just make sure that this is one single function. So now this is one single function. So to use this single function, which is not a part of TensorFlow, we need to use a function from TensorFlow called NumPy function. So first, this function takes the name of the function, input for the function, and the data type. What is the data type they give back? Float 32. And just write tf.float32 here, .np, because NumPy is working till I think here, but in this NumPy things don't work. So it's gonna give you back X and Y. Now we need to put some shape of these X and Y. So we're gonna say X dot set shape, height, width, and number of channels, Y height, width, and 1 as number of channels. So this is the second last function. Now we have one more function called tf_dataset, which is the main function. So what it take X and Y, this X and Y is basically list of images and mask, a batch size, default value 2. Then we have this entire code, and if you see this tf_parse code is used here. So what it do, it is used to map those list into specific batches of images and labels. So we are done with the data processing part completely. Now we'll build train dataset and validation dataset pipeline for training and validation. So this is done. We have trained dataset. We have called this tf_dataset function. We have given training images, training labels or ground truth. We have set the batch size. So basically we have overridden the value of 2 to 8. Same we have done with the validation dataset. Now we need to build the model. So we're going to say model is equals to build unit. Now it's up to you which what square net you want to use. I want to use the main. You can use the light one. Now we're going to compile it. First would be the loss. So here we're going to use binary cross entropy. Actually this binary cross entropy is also utilized in the original paper as I remember it. If I'm wrong, please comment it down. And I hope you're like enjoying the video, maybe getting to learn something from this. So if you learn something from this video and you find it useful, then please make sure you subscribe the channel and hit that bell icon. You can also support the channel by joining membership or by super thanks or any other name. So it's just a choice. It's not compulsory always. Just simply subscribe it. That is also a help. Now we have callbacks. So callbacks are basically some functions which are used during training. So during training we cannot like do anything, we just need to wait. So let's say we want to save wait file, so these in that case check callbacks come as help. So we have 4 callbacks here. First is this model checkpoint. So it basically done, what it do is it saves your model wait file. Then we have reduce LR on plateau. It decreases the learning rate when your loss stops to decrease. Then we have CSV logger. It basically write all the training and validation values in this log.csv file. And at last we have early stopping. So what it does, let's say for a continuous of 20 epochs, the validation loss does not improve, so it would stop the training. So what it does, it basically stops the training when it stops improving, because we don't want our resources to be wasted and utilized and we do not get any improvement. Because when you train your GPU, especially mine, reaches near about 80 and 82. Yeah, 82 is the maximum. So if there's any experienced developer here, just do tell me if this temperature is normal 82. Okay, and I don't have an AC in my room. I usually don't like it. So just do tell me, do recommend me something if you feel this is high enough. Because see, the GPU is really expensive and I don't want to burn it. Okay, because it's I cannot buy it for now second piece. It's really expensive. Okay, so let's leave the GPU aside. Now let's move on to the training part. Okay, let's wait. I already have a wait file. Okay, let me stop it here. So you can see, if I show you, this is the loss, this is y0, y1, y2, y3. So like this we have till y6. Okay, so this is how the training would begin. We can ignore it because I already have a wait file, so you don't need to worry about it. And now what we'll do, we'll work onto the test case. So let me just, okay, let me show you. So here you can see I have this is the wait file. Let me copy it here and we'll use it. I already trained it on few epochs. Yeah, and I think it's gonna give us some decent performance, and I'm not saying it's going to be really good, but it's going to be decent performance, so that you can have a look at it, what we are trying to achieve. You can further improve its performance. Again, we're gonna set the same height and width as we used during training. Again, same function to create folders. Now again, we're gonna seed the environment. So we're gonna use same seed number so that we have same randomness. Now we're gonna save the mask. If you remember, we have near about seven masks. So what we're gonna do, we're gonna have 2 folders for each prediction. First, where we would save all the masks and we can observe them, how one mask is different from another. And second, we're gonna apply this prediction with the original image and see how it's performing. So we're gonna create a directory for storing files. So here we are creating basically this results folder, and inside it we have 2 subfolder called joint and mask. Here you can see we do not have any directory called result. So let us run the test and you will see. You can see a results directory. Inside you have joint, which is blank, mask, which is blank. So let's move forward in our work. So next we are going to load the model. You can see the model path. Then we're going to load the model. Now let's say model.summary. Let me check if it is working or not. Okay, you can see it's working. So we'll utilize this to test. Okay. I also have some test images for testing. Okay, let me show you. So these are some of the images which I've downloaded from, I think, unsplash.com. That website provides really great huge resolution images. So you can see these are really huge images. These are some of the samples. You can use it on your own projects which can have different image, but make sure those are images of human only because if you use any other image, I think it won't give you perfect result, as it is trained on human images only, so it would work perfectly on human images only. Okay, so we have loaded the test images. We're gonna print how many there. So let's run it and see how many images we have. I think we have 19 to 20 images. That is what I remember. Okay, we have 19 images. I think these are okay just to test. Okay, so now we're gonna work on to the prediction part. So I'll write this code because this is the important code. I'll write it myself. For X in TQDM. So TQDM is basically a progress bar. Let's say we are working on a for loop. Let's say and like when the loop is working, it's gonna take some time. So in that case, we don't know how many iterations are done, how many are left, how much time it's gonna take. So in that case, TQDM comes really help. It's a progress bar which shows that out of 100 iterations, out of 100, 10 iterations are done and 90 are left. So I'm going to loop over all the images, the list of all the images paths. So first of all, we're going to extract the name. Okay, let me show you the path. First, we're going to show you the path. Okay. Yeah, little mistake I've done. Like this is what happened when you don't, or when you are not focused. Okay, you can see 19 images and their path, and this is the progress bar because we are having 19 images only, so it's really fast. So what we need is this name because we are going to save some images, and to save we need the name. So make sure we have corresponding name as the image. We're gonna extract this. See, this is a slash which is in Linux environment, but in Windows it would be, I think, this would be your path. So when you're extracting the name, things would be a bit different. So what I'll do, I'll explain you the entire logic here. So let's say output would be name. So we're gonna split this first. See here, my path is having this slash. So this slash differentiate between the different directories and folders. So I'm going to copy this and paste it here. So if you are Windows, so this would be your path. Just first see it and then put it here. So I'll break it here. Okay, so we have name. So name would be a list. You can see test, and we have this name with extension. Now how much long your path would be, the name would always be in the last. So what we can say is -1. So now we would have the name with extension, and this is fine. We can use this name and extension. Let's say you want to extract only the name. So what you can say is split dot. Again, you're going to split this string into two parts. First name and then extension. So I hope you get the concept here and hope it would work fine for you. Now we're going to read the image. Okay, so I'll directly copy paste it because this thing we have already studied in the training part. So we're going to read the image as RGB. We're going to resize it. We're going to normalize it, and we're going to expand its dimension. So now what I'll I'll just show you the difference between both before and after expanding dimension. See the difference between what the difference is there. See, this is the image, and like in deep learning, in this TensorFlow and every other deep learning stuff, we give in images, the images, we give batch of images, because here we have only one image, so our batch would only have one image. Okay, let me minimize my sound. Okay, so this is the difference what it makes. So your batch is only have one image, so your mask, so the group of mask would only be predicted for this one image only, and that group of mask can have multiple masks, or it can be one mask. Now we're going to move on to the prediction. So if we first going to say pred model dot predict x as the input, verbose 0. So now if you remember, we have 7 masks, not one. So this is just all of the mask into this. So first of all, let's me print the shape of this pred, so that we have an idea what is the shape and we can work on this. Okay, so it's a list. Got it. It's a list, so it cannot be a shape. Okay. So first, what we're gonna do, we're gonna join all these 7 masks. Okay, and save them. So what I'm gonna call it, pred list. This is a new list. So we're gonna say for item in pred. Now pred is a list, so we're gonna iterate over it. So let me print the shape of item. Now I hope I will get some shape here, because without knowing the shape, it would be a bit difficult, not that much difficult. Okay, you can see 1 2 3 4 5 6 7. So we have 7 masks here. You can see these are also in batches, but each batch we have only 1 mask. So now what we're gonna do, we're gonna say p equals to item 0. So we're gonna multiply it with 255, because the output is a sigmoid. If you see this, output is sigmoid, so it gives a value in between 0 and 1. So to visually see it, we need to multiply it with 255. And now the shape is something like 512 by 512 by 1. So now what we can do, let me just concatenate, should be small. So we're going to concatenate these masks on top of each other on the last axis. So it would shape something like this. Okay, so we have changed the number of channels here. Now we're gonna say pred list dot append p. Now one more thing, because we are going to we're gonna join all the masks, okay, one after other, so there should be a separator in between them. That should be a simple line. So what we're gonna say, line is equals to np dot ones, it will be height, then 10 and same number of channel. Now what we're gonna say, pred list dot append line. Done. Now we need to save this pred list. So first we have save image path, where we're gonna save it. So we're gonna save it in the results folder inside the mask with the name we have extracted here. Okay, now we have this list of images, so we're going to concatenate them. On the axis 1, and now we're going to save the images. Save image path, cat images. Okay, let's run it for one, and then we're going to run it for all. Okay, it's done. Let me show you YT results. A joint. So joint is blank. We saved in the mask. Okay, you can see first one. If you go from starting to end, the quality of this the prediction decreases, because the first one is really good, then a bit less than good, then a bit less than good, and finally we have come at the last mask, which is a bit rough. It is good if you consider it as segmentation task, but we need finer details. Okay, this is the issue. So you can see we have finer hair structure here, and this is the difference. This is what the difference between a segmentation task and a image mating task. So now what we'll do, we'll use this final mask, okay, and apply it over the input image. Okay, now let's work on that. So we're gonna say it, save final mask. So final mask is y0, that would be print 0 and then 0. So let's resize this y0 as the input image. Okay, before that we need to extract the height and width of the image here. And these images are really huge resolution images, like up to 1500 or 2000 pixels also we have. So let's say y0, then again image width, then image height. Now I'll print the shape of y0. Before and after we'll print and see the difference. You can see the difference. First is 512 by 512, and after resizing it's about 1300 by 13,000 by 2000. So you can see this change, this increase in the size would also deteriorate the quality of your predicted mask. Okay, but still we'll get good result, I think. Not that good, but in terms of saying good, it's just good only, not that good, or it would not be that bad. Now here you see we don't have any number of channel here, so we're gonna expand its dimension. Now we'll have some lines of code here. So this is a line which separates. Okay, so what we have, first we have image, original image, we have a line in between, we have this resized final fused mask, then a line, then image multiply with this prediction. Then we're going to save it and let's run it for now. And these are the test images which are not taken from this dataset but from a different website. So let's see how it performs. Okay, so this is done. We're going to go into the results folder, joint. Okay, let me zoom it. So here if you see the size, 6000 by 1300. You can see, if you see the image and the and this, you can see it's really well, it has removed the background really well. It has, if you see a few details, you can see this here in between space, which is not removed here properly, and that is because I haven't trained this model really on a huge number of epochs, because that would take huge amount of time and the video would take even a month to come. Okay, so this is just to show, this is just okay one example. So what we'll do, we'll remove this break from here and let it run for all, and we're gonna see how it perform. you all can also use this program and build your own project and do comment out the link of your projects if you have uploaded them somewhere on GitHub or other places. Okay, so where's our folder? Okay, not this one. Yeah, this one. Okay. Okay, this is well. Okay, see, the best thing about meeting is that, see, these fine details are really well presented here. You see, like some are missing. That is just because the training is not done well. But still, these this is really good. Actually, this the background is white, so this is would be really well. But even if you see this, observe, see, there's a small space here which represent background, and here you can see the model is trying to learn. If I like train it more, I think it would have easily grasped. You can see, this is the thing about the image mating, which the segmentation model is not built for. You can see it's the small hair from the beards are also got well, but this part of here is like is like suppressed a bit, but that is good because somewhere it's gonna drop, somewhere it's gonna give you good. So it's up to you how you're gonna optimize it. Like for me, this is good because it hasn't been optimized, well trained. I think this example is best. You can see really well details about the hairs. Yeah, this one is really nice example. So I hope you have understood the all the things here, and you will present it. You will use it somewhere where you're gonna need it. So ultimately, I mean, I hope this video helps. For now, the last question is how to improve it further. So first, you can train it on more epochs. You can increase the input size. If you see, input size is also having an effect, because when you resize the image, you lose details. Let's say you are having an size of 512 by 500, you increase it to 5000 by 5000. So now you can see the noise we add into the image, the quality we lose. So maybe you can increase the image resolution and train it further. If you see, I haven't applied any data augmentation technique. You can apply them. You can try some new loss function to further improve the performance. You can see what is the latest state of the art in image mating and work on that. So if you have any new idea about how can I improve it further, please comment it down in the comment box. So thank you for watching the video. If you have any question, do email me. Follow me on Facebook, Twitter, LinkedIn, everywhere. And please don't forget to like, share and subscribe the video. Thank you. Have a nice day.